Hi everybody, happy Wednesday. We're going to go through our next lesson in Unit 8, and today we're going to be talking about using proportionality theorems. So the first theorem we're going to take a look at is triangle proportionality theorem, which is also called the side splitter theorem. And what this theorem tells us is if we have a triangle and we have a line that intersects two sides of the triangle and is parallel to one side of the triangle, it's going to divide the two sides of the triangle proportionately. So what we have here is triangle ABC, and we have segment DE intersecting two sides of the triangle. It is also parallel to the third side of the triangle. Those little arrows are parallel symbols. So what this tells me is DE is going to be splitting each side into two parts. So DE splits this side into two parts. It also splits the second side into two parts. Those two parts are going to be proportional to one another. So the first part here on the one side is BD. The second part on the first side is AD. So that ratio is going to be equal to the ratio of the two parts of the second side. So the first part of the second side is BE. The second part of the second side is EC. So when we see this set up here, we're going to set up a proportion with ratios of the two parts of each side of the triangle. So if we move to the next example, it says find the length of PQ. PQ is here. We want to find the length given TQ is parallel to SR. So we have a triangle, we have a segment intersecting two sides of the triangle, and it's parallel to the third side. So TQ breaks up the first side into one part and two parts. TQ breaks up the second side into one part and two parts. So we're gonna set the two parts, we're gonna put the two parts into a ratio and set them equal to one another. So the first part of the first side is 14. The second part of the first side is 6. We're going to set that ratio equal to the two parts of the second side. So x over 9. I know that I could simplify 14 over 6 because both of those numbers are even. So if I take out a common factor of 2, that's going to leave me with 7/3. You could cross multiply if you want to, or use equivalent fractions. I know that to get from 3 to 9, I have to multiply by 3. So if I do the same up top of the fractions, 7 times 3 would get me 21 for this spot. So x would have to be 21. X is the length of PQ, so my answer is 21 units. I'm going to do a couple more examples here using this side splitter theorem. So in the next example, we want to find the length of AE. So AE is here. So again, we have now a triangle. We have a segment parallel to the third side, and this segment is splitting the other two sides proportionally and splitting it into two different parts. So on the first side, we have the two parts. On the second side, we have the two parts. So I'm going to set up a proportion with the two parts of each side. So on the first side, we have the first part being 5, the second part being 3. On the second side, we have the first part being x, and the second part being 4.5. On this one, I am going to just go ahead and cross multiply because I have some decimals here. 3 times x will get me 3x. 5 times 4.5 will get me 22.5, and if I divide both sides by 3, I'm going to get that x is equal to 7.5. So x, again, I let be the length of AE. So AE's length is 7.5. Now, using the same diagram for number 3, we want to find the length of BC. So I'm just going to label that with a different variable. I'm going to label the length of BC y. That's the next thing we want to find. Now, y is the length of the third side of the triangle. So we're not going to be using the side splitter theorem here. We're actually going to be using similar triangles. The small triangle and the large triangle are similar by angle. They both share angle A. Because we have two parallel lines and a transversal, we also have a pair of corresponding angles. So the small triangle and the large triangle are similar to one another. So what we want to do in order to find the length of BC is we want to set up a proportion that compares corresponding sides. So DE, the side length of 4, corresponds to the side length of BC, which is y. So again, when we use similar triangles and we set up a proportion, we want to compare corresponding sides. So 4 is a full side, y is a full side of the two triangles. Now next, I'm probably going to work with this other side because the other side doesn't contain any decimals. So in the smaller triangle, AD has a length of 5. So I'm writing up top of the fractions the smaller triangle side lengths. Now in the larger triangle, the side that corresponds to AD is not just DB. From D to B, this is not a full side of the triangle. So we need to compare 5 to this entire side length. So 5 and 3 added together is going to get you a length of 8. So 5 corresponds to AB, which has a length of 8. Again, for this, we're not using side splitter theorem. When I go ahead and I cross multiply now, 4 times 8 is going to get me 32. 5 times y will get me 5y. If I divide both sides by 5, I could leave it as a fraction, 32/5. I could also change it to a decimal. So either 32/5 or 6.4 will be our answer for the length of BC. All right, for the next one, it says, given QS is parallel to PT, so we have parallel segments, find PT's length. So what again I need to do here is I want to find the length of PT. I'm going to let this be y because I'm already using x to represent something. So I'm going to use just a different variable to represent the length of PT. And PT is the third side of the triangle. So I want to eventually use similar triangles in order to find the length of y. In order, though, to use similar triangles, I need to be able to find a full side length of the large triangle, which I'm unable to do at the moment. I don't know this side. I don't know what x is or what x is. So I need to first use side splitter theorem. So again, I'm going to be looking at this segment that divides two sides of the triangle proportionately. So QS is parallel to the third side. It's going to split the first side into 2 parts. It's going to split the second side into 2 parts. And I'm going to create a proportion with the 2 parts, or first a ratio, with the 2 parts of the first side, set that equal to a ratio comparing the 2 parts of the second side. And I'm going to go ahead and I'm going to cross multiply to figure out what x is. So my first cross product, I need to multiply 9 by the quantity x minus 2. The second cross product, I have to multiply 4 by the quantity x plus 3. So I'm just going to distribute. If I move 4x to the other side by subtracting, over here I'll get 5x. If I add 18 to both sides, I'm going to get 30. So I know that x has to be 6. So 6 plus 3 would get me an entire side length of 9. 6 minus 2 would get me an entire side length here, or an entire segment length, I should say, of 4. So again, what we're really interested in is finding the length of y, pt. So in order to do this, I now need to use similar triangles. So I'm going to set up a proportion that compares corresponding sides of the two triangles. So I'm first going to be taking a look at the first little triangle. So I see the side length of 7. 7 corresponds to the same side here down here, pt, which is y. And then you could pick either of the two other sides of the triangle. Maybe we go ahead and choose RQ's length. The smaller triangle has a side length of 9. Again, when we're using similar triangles, we want to use full side lengths. So this entire side length that corresponds to RQ is RP. 9 and 9 gets me an entire side length of 18. You could cross multiply. I noticed that 9 over 18 is going to reduce to a half. If I use equivalent fractions up top to get from 1 to 7, I had to multiply by 7. So if I do the same thing in the denominator, 2 times 7 is going to get me 14. So y would have to be equal to 14. Now, the next theorem, or the last theorem for today that we're going to be talking about, is the converse of triangle proportionality theorem. So it's a converse, just again means in a hypothetical or in a, conditional statement, in an if-then statement, we are flipping the if and the then. So this theorem says if a line divides two sides of a triangle proportionally, then it is parallel to the third side. So if we know that two pieces of a side of a triangle are proportional to the two pieces of a second side of a triangle, it means that this segment that is splitting the two sides proportionally has to be parallel to the third side. So what we would be concluding is that segment DE has to be parallel to the third side, or segment AC. So we're going to be using the converse of triangle proportionality theorem for our last several examples. So for 5 and 6, it says determine if segment DE is parallel to segment BC. Show work and explain your answer. So if DE is parallel to BC, it has to be that DE splits the two sides of the triangle proportionally. So again, I want to show that if DE is parallel to BC, it's going to split these two sides into equal ratios. So I'm going to compare 7 to 2, the two parts of the first side, and I'm going to compare that to the two parts of the second side, 8 over 3. Now, if these are proportional, we should have equal ratios. I can't reduce 7 over 2 anymore. I can't reduce 8 over 3 anymore. So 7 halves and 8 thirds are not the same fraction. Since they're not the same fraction, it means they're not proportional. And because they're not proportional, it means that these two segments cannot be parallel to one another. So we're going to take a look at the next example. So again, we want to show or figure out if DE is parallel to BC. So if DE is parallel to BC, DE is going to split the two sides of the triangle into two parts that are proportional to one another. So the two parts of the first side, I'm going to compare 6 and 9 in the same ratio. I'm going to compare that to the two parts of the second side, which are 4 and 6. And if they're proportional, these two fractions should simplify to the same ratio. So I can simplify 6 over 9. If I divide out a common factor of 3, I'll get 2/3. I can simplify 4 over 6. Both numbers, top and bottom, have a common factor of 2. So if I divide those out, I will get 2/3. Since 2/3 does equal 2/3, DE does split the two sides of the triangle proportionally. These are proportional because they simplify to the same ratio. So we would say that DE is parallel to BC. And then the last example we're going to take a look at says find the value of x so that HJ is parallel to GF. So we want to guarantee that HJ is going to be parallel to GF. So if we want to make or prove these parallel, HJ has to split the two sides of the triangle proportionally. So HJ would have to split the first side into two parts that are proportional to the other two parts of the second side. So I'm going to create a ratio of the two parts of the first side, so 32 over 30, and that should be equal to the ratio comparing the two parts of the second side, which are 3x plus 9 and 5x. So the numbers here, 32 and 30, are a little bit large, so I noticed that they're both even. So the first thing I'm going to do, just to make the numbers I'm working with a little bit smaller, is I'm going to divide out a 2 and a 2 from the top and the bottom of this fraction. And then I'm going to go ahead and cross multiply. So if I multiply 16 by 5x, I'll get 80x. And then I have to multiply 15 by the quantity 3x plus 9. So I have to distribute. 15 times 3x would give me 45x. 15 times 9 will get me 135. I need to combine my x terms, so I'm going to bring 45x to over on the left. I'm going to bring that to the left side by subtracting. If I subtract 80 minus 45 is going to get me 35x equals 135. Now, 35 does not go into 135 evenly. If I were to divide this out, it would be about 3.86.